All right. Good morning, everybody. New week, new chances to get better. So, to start today, um, let me do some quick announcements here. Then we will pick up where we left last week. Okay, some important announcements for this coming week. We will have in-class assignment this coming Friday, okay, on the 12th. And do not forget that you have online homework for chapter 2, part 1 due on Thursday night, okay? All right, so with that being said, let's see where we left off on Friday. Okay, so what I showed you on Friday was to how to fill up the shells and subshells for any kind of element. So let me switch to the other screen here. And you can see the notes. Okay, so we did together for sodium, and we concluded that sodium has 3 shells and 1 valence electron. Okay, and we started setting up for potassium. Okay, so far we know that potassium has 19 electrons. The next step is to figure out how these electrons are organized in the shells and subshells. Okay, so the first step here is always to determine the number of electrons. Pay attention to the charge of the element, okay? To make sure you get the right number. Now that we know that we have 19 electrons, let's distribute these electrons among the shells and subshells. Always start from the lowest energy subshell, which is always going to be the 1s. In this case, we are going to put 2 electrons in the 1s shell because that's the max capacity. Moving on to the next subshell to be filled, that's going to be the 2s right here, okay? So we are going to put 2 electrons. So far, we have 4 electrons. After the 2s, go back to the top and get the diagonal again. So you start filling up from the beginning of the arrow, which is the 2p shell. Then we are going to have 6 electrons here. So far we have 2 electrons in the first shell, 8 electrons in the second shell. So that's a total of 10. There's still 9 to go. After the 2p, the next subshell to be filled is the 3s. And we are going to put 2 electrons there. So that's a total of 12. After the 3s, go back to the top and trace the diagonal again. Next one after the 3s is the 3p shell. And here we are going to have 6 electrons. So far we have 18. So we are very close to get the 19. Attention here, okay? After the 3p, if you follow the diagonal, the next subshell to be filled is the 4s. And we just need 1 electron in the 4s, okay? So pay attention to the order that you are filling. So third shell has also 8 electrons and the fourth shell has 1 electron. If you count the total number of electrons, you are going to get 19, and that has to be equals to what you predicted in the beginning. Okay, so I need you to pay attention to the order that you are filling up the shells and subshells. So for potassium, we have 4 shells with electrons, and the number of valence electrons in this case is the total number of electrons in the last shell, which is 1. Okay, so therefore potassium has 4 shells with electrons and 1 valence electron. And that's how you distribute the electrons among shells and subshells. Okay. Unfortunately, I don't have time here to show more examples, but I showed you the basics. And if you follow this strategy, you are going to be able to draw the electron configuration for any kind of element. Okay. All right. So let's look here one more thing. If we look at the electron configuration of sodium, we saw that we have 3 shells with electrons and 1 valence electron. If we look at potassium, now we have 4 shells with electrons. However, we have something in common to the sodium, which is 1 valence electrons, okay? So although sodium and potassium are different elements, they share the same number of valence electrons, which is 1. If we go back to the periodic table and locate the elements sodium and potassium in the periodic table, we are going to find out that sodium is right here. Sodium is in the first column of the periodic table and the third row. Okay? Third row and first column. Potassium is right below sodium in the fourth row and first column. Okay, fourth row and first column. If we try to correlate these two numbers with the electron configuration, what's the obvious conclusion? Sodium has 3 shells and 1 valence electron. Potassium has 4 shells and 1 valence electrons. Sodium is located in the third row and first column, and potassium in the fourth row and first column. Therefore, the number of the column is always going to be equal to the number of valence electrons. Okay? The number of the column is always going to be equal to the number of valence electrons. And the number of the row is always going to be equal to the number of shells. Therefore, just looking at the location of the element in the periodic table, we must be able to tell right away the number of valence electrons and the number of shells. Okay, so with all this information together, you understand why each element is located in a determined spot in the periodic table. And also you can tell a lot about the electron configuration just looking at the periodic table. And then sodium and potassium.
What?
Any questions?
Back on the floor.
Sorry, is there a question here? Okay, I think there is no question. So although sodium and potassium are different elements, they share the same number of valence electrons, and the chemical properties are basically determined by the number of valence electrons. And that's why they are grouped in the same column. Okay, just one trick here when we are looking at the number of the group in the periodic table. When we are between the groups 13 and 18, to determine the number of valence electrons, you have to subtract 10, okay? So between the columns 13 and 18, to determine the number of valence electrons, you must subtract 10. Okay, so we have a question here. How do we know if an element is neutral? Okay, so Emma, what you are going to look for to determine the charge of an element is the number on the right top corner after the symbol of the element. So for example here, if we have calcium, and there is no number here, okay? So that means is neutral. If there is a positive charge, that's going to be indicated like that. So now we have here a positive net charge. And if there is a negative charge, then that's going to be indicated like that. Okay. So always look at the top right corner after the symbol for the element. Okay. No number, that means neutral. 1 plus positive, for example, and 1 minus negative, for example. Okay. Thank you for your question. Okay, So why do we subtract 10 from columns 13 and 18? Andrew, I will get there maybe by the end of the day today or on Wednesday. Just give me some time. Is there a symbol for valence electrons? No, there is no symbol for valence electrons. Okay, so right now we are at a very, very good point that we can determine a lot of properties just looking at the element and locating it in the periodic table. So let's move on. Okay, so let me switch screens here. Okay, so just to be more organized, the number on top of each column in the periodic table is named group, and the number of each row in the periodic table is named period. Okay, so some better names instead calling columns and rows. Okay, the number on top here is called group, and the number on the side is called period. And remember, the number of the group is related to the number of valence electrons, and the number of the period is related to the number of shells. All the elements that are in the same group, they share common chemical characteristics, and they have some specific names. For example, here, the group 1, they are called alkali metals. And one thing that I need you to pay attention is that hydrogen is not part of the group 1, okay? So hydrogen is here, but does not belong to the group 1. The group 2 receives the name of alkaline earth metals, and etc., 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 all the way to the group 18, which are called noble gases. One important thing here, the elements between the atomic number 57 and 71, they are squished here. Those are the lanthanides, and between 89 and 103, those are the actinides. All right, very good, very good. Always remember that the number of the group corresponds to the number of valence electrons. Attention, when you are between the groups 13 and 18, you must subtract 10 to get the number of valence electrons. And the number of the period corresponds to the number of electron shells. And that's the rationale behind the organization of the elements in the periodic table. Yes.
Um, so I was just would like some clarification about the transition metals.
Mhm.
Where do you subtract 10 from? Is it just from their, I mean, that would make sense to transition subtract it from the column number because then you'd have negative numbers, but um, where do you subtract the 10?
Okay, so let's see one thing here. So if you are between 13 and 18, that's
Mhm.
where you subtract 10.
Oh, I misheard you. I thought you said
Okay,
between 13 and 2. It's fine. Yeah. Okay, that
okay,
makes sense.
okay,
Yeah.
okay, all good?
Yes, all good.
Okay,
Thank you.
yes, yes. So let's answer the question earlier. The reason why you subtract 10 here, we can do this in the discussion, but once you overcome the transition metals, you start to fill up the d orbitals, and the maximum capacity of the d orbitals is 10, and that's why you are going to subtract 10 when you move to the right side here. So maybe we will do some problems in the discussion, and then you can clearly see that when you move up to this side here, you have 10 extra electrons that you will just discount just to get the number of valence electrons, okay? So it's just a trick, basically. Okay, so of course, I will not ask you to name each group of the periodic table because that doesn't make any sense. We can go back to the book and look at the names, and you don't need to know this by heart. I need you to know that the number of the group belongs to the number of valence electrons, and the number of the period corresponds to the number of shells. Okay, so another way to divide the elements in the periodic table is by classifying them in metal, metalloid, and non-metal. Okay, so all the elements in blue are classified as metals. All the elements in yellow are non-metals, and a small chunk of elements between the metals and non-metals, they are classified as metalloid. Metalloid means that they may behave as metal or non-metal depending on the situation. All right, so just recapping here. Uh, in the periodic table, we organize the elements starting from the lowest atomic number and going all the way to the highest. This number on top of each column is called group. Elements in the same group, they have similar chemical properties. And the number of the period, or also the rows of the periodic table, uh, is the number of electron shells. Remember, the trick to determine the number of valence electrons when we are talking about elements from the group 13 to 18 is to subtract 10. Okay? For all the other cases, you don't need to do that. Okay, so now that we know how to determine the electron configuration for any kind of element, always pay attention to the charge to determine the correct number of electrons. You can just look at the periodic table and determine the number of valence electrons and also the number of electron shells. So now it's a very good point to start talking about trends in compounds formation. Most of the compounds in nature are found as combination of different elements. For example, potassium by itself is highly unstable and reacts violently with water, while salts such as potassium carbonate or potassium chloride are extremely stable compounds. Okay, so what is the driving force that directs the formation of compounds, and why most of the elements are not stable just by themselves? So if we go back to the periodic table and look at all the elements, almost all of them will be found in nature as a compound, okay, combined with other elements. However, there is one group of elements that are found isolated in nature. Just the fact that they are found isolated in nature, that tells us that those elements do not need to combine with anyone to achieve stability. They are stable by themselves. And those elements are called noble gases, and they are the elements from the group 18. Is the far right column in the periodic table. Okay, so they are noble because they do not mix up, they do not react or combine with other elements. They are just stable by themselves. Okay, so every time we find in nature something that's stable, chemically stable, we are going to investigate this family of elements and see what does it make them to be stable. So let's look first at the electron configuration of all those elements, okay? So we are talking here about helium, neon, argon, krypton, xenon, and radon. Okay, 2, 10, 18, 36, 54, and 86 are the atomic numbers. If we look at the electron configuration of all of them, that's what we are going to observe. Okay, so for now, I want you to forget helium for a moment, and let's focus our attention to neon, argon, krypton, xenon, and radon. If we look at the valence shell, what is the common characteristic that we find for all of them? Let's start with neon here. The electron, sorry, the valence shell here has 8 electrons, argon 8 electrons, krypton 8, xenon 8, and radon 8. Okay, so all of them share the same characteristic, excluding helium, which is 8 electrons in the valence shell. Well, if they are stable and they have all 8 electrons in the valence shell, what's the obvious conclusion? Any element will lose or gain electrons to acquire the stable noble gas electron configuration. In other words, is 8 electrons in the valence shell and that's called octet rule. Okay, so think about that every element wants to be a noble. To be noble means to have 8 electrons in the valence shell, and that is called octet rule. Okay, so now our goal is not only to determine the electron configuration, but predict if an element will lose or gain electrons to achieve 8 electrons in the valence shell, okay, to obey the octet rule. Okay, so let's start with an example here. I will do that with you, and then we will get the rationale here, how to determine when an element is losing or gaining electrons. Okay, so the question here is to determine the most likely charge of the following elements. So let me quickly switch to my other screen here, and I can write things. Okay, so always to determine the most likely charge for an element to achieve stability, the first step is to write the electron configuration. So let's start here with potassium. Potassium is right here. Okay, so atomic number is 19. Potassium by itself has no charge. Therefore, the number of electrons is equals to the atomic number. Now that you determine the number of electrons, you can do the electron configuration. So we already did that. So I'm just going to rewrite what we already did here. So that's going to be 1s2, 2s2, 2p6, 3s2, 3p6, and 4s1. Okay? So looking at the electron configuration, you can figure out if potassium is stable or not. Remember that stability means 8 electrons in the valence shell. Okay, attention to that. 8 electrons in the valence shell. If we look at potassium, what's the number of electrons in the valence shell? Just 1. Therefore, potassium is not stable by itself. So to be stable, it has to have 8 electrons. So somehow we have to find a way for potassium either to gain electrons or to lose electrons and achieve stability. So if you just have one electron in the valence shell, one way to get 8 is to add 7 electrons. So we have one way to achieve stability by adding 7 electrons, and then you would get to 8 electrons in the valence shell. However, look at the electron configuration of potassium. Look at the shell right above the valence shell. How many electrons do you have there? You have exactly 8 electrons. Therefore, if this element loses just one electron, this shell is going to be gone. And now the new configuration is going to be 1s2, 2s2, 2p6, 3s2, and 3p6. Look at that. Now we have 8 electrons in the valence shell. We achieved stability. To achieve stability, we had to lose one electron. Therefore, the potassium is not neutral, is no longer neutral. Potassium has now a charge of 1 plus, and that's how we are going to symbolize that. Okay, recapping here. The potassium now has a charge 1 plus because it lost one electron to achieve stability, okay, to get the noble gas configuration. So you don't need to do the electron configuration all the time. You can look at the number of valence electrons and figure out if it is easier to add electrons to complete the octet or lose electrons in order to complete the octet. For potassium, we have two options, either add 7 or lose 1. Which one is easier? Lose 1 is much easier than convince someone to give you 7 electrons. Therefore, potassium is stable when potassium has a 1 plus charge. And that's the most likely charge for this element. Okay, so let's see the second element here in this example, bromine. First thing is to locate bromine in the periodic table. So look here at the group 17. Oops. Bromine is right here. Bromine has atomic number 35. There is no charge to this point. Therefore, we have 35 electrons. And now I'm going to use the trick of determining the number of valence electrons just looking at the group. So bromine belongs to the group 17. Remember, when you are between the groups 13 and 18, just subtract 10 to determine the number of valence electrons. Therefore, the number of valence electrons for bromine is 7. Okay, bromine by itself has 7 electrons. First question, is that a stable electron configuration? To be stable, we must have 8 electrons in the valence shell. 7 is so close to 8, so close. So there's always 2 options. You either add electrons to complete 8 or lose all of them. Those are always the 2 options. For bromine, the easiest option is to just add 1 electron, and then we get to the noble gas configuration. Therefore, when we add 1 electron to the bromine, that will complete 8 electrons in the valence shell. And now we have 1 electron in excess. Therefore, bromine 1 minus is stable. Okay? So because we had to add 1 electron, we have an excess of 1 negative charge. Therefore, we will represent this excess by this number on the top right corner of the element, which means bromine minus is a stable compound, okay, or stable element. Bromine by itself is not stable. That's what I want to say here. Okay, so now let's look at oxygen. Oxygen right here, top of the group 16. Atomic number for oxygen is 8. Oxygen by itself here is neutral, therefore 8 electrons in the valence shell. Let's determine the number of valence electrons, and I will use my trick to just look at the number that this element belongs to and figuring out the number of valence electrons. Okay, so oxygen is from the group 16. Remember, to determine the number of valence electrons when an element belongs to the group 13 all the way to 18, we subtract 10, and that will give us the number of valence electrons for oxygen, which is 6. First question, is oxygen stable by itself in when we have a neutral charge? The simple answer is no, because to be stable, we must have 8 electrons in the valence shell, and in this case, we just have 6, there is always 2 options, guys. Either lose all of them or add electrons to achieve 8. In this case, we can either add 2 electrons or lose 6 electrons. The easiest way is to add 2 electrons. 6 plus 2, 8. Now we have stability. Because 2 electrons were added, that means we have an excess of 2 negative charges, and I'm going to represent that by 2 minus right here. Therefore, O2 minus is stable. O2 minus is stable because it has 8 electrons in the valence shell. Okay, so we are always going to deal with the valence shell. And that's where 95% of the chemistry reactions happen. Okay, the valence shell is the most exposed shell and are the ones that can lose or gain electrons. Okay, we are running a little bit short on time, so I will not have time to go into a detailed resolution for magnesium or nitrogen. So I will give you the answers. Magnesium is right here and belongs to the group 2, which means 2 valence electrons. To achieve stability, magnesium is simply going to lose these 2 electrons and becomes magnesium 2 plus. And the final example, nitrogen. Nitrogen is right before the oxygen, okay, group 15. Therefore, 5 electrons in the valence shell. To achieve stability, is easier for the nitrogen to gain 3 electrons. 5 plus 3 is 8. In exchange of gaining 3 electrons, nitrogen will receive a charge of 3 minus. Okay, so what I'm trying to tell you here is that we need to be able to figure out what is the charge that the elements are going to get in order to achieve 8 electrons in the valence shell, which means stability. Okay, always follow the noble gas configuration. There is no lunch for free, right? So if you are gaining electrons, someone has to give you electrons. And that's the driving force to form compounds. If bromine needs to gain electrons, someone needs to give those electrons, okay? And that's going to be the next thing that we are going to do on Wednesday. So we are going to look at 2 elements, sodium and chlorine. Let's figure out if they need to gain or lose electrons, and let's see if they are compatible, if they can get together and form something stable. So with that being said, I think that's more than enough for today. I hope you have a good week, and I will see you tomorrow. Okay?
Thank you, George. Have a great day.
Bye-bye.
Thank you.
Can I
Thank
step away?
you. Have a good day.
Thank you, Professor.
Bye bye.